Let's talk about the mean value theorem. The mean value theorem is truly a cornerstone theorem for several other theorems and applications that we'll be using in this class and other classes beyond Calculus 1. To start talking about the mean value theorem, we need to begin with a discussion of Rolle's theorem. Rolle's theorem says if f is a continuous function on the closed interval from a to b, and f is differentiable on the open interval from a to b. Remember, by the way, differentiable means that the derivative exists. And finally, that f of a is equal to f of b. Then we know that there exists at least one x value, let's call it x equals c, such that f prime of c is equal to 0. So let me show you a picture of this before I show you a proof. And I'm going to leave the theorem up here. So let's say that we had, give ourselves some separate room here. Let's say that we had this graph. So I'll do the y-axis and the x, and the x-axis. There we go. And I'll draw in a curve where, okay, this is the important part. So I have to have x equals a represented. I'll put it there, and x equals b over here. And I need to draw in a continuous function on the closed interval from a to b. So when I draw in this function, no skips or breaks. I need to draw a differentiable function on a to b, so no cusps or corners. And here's the weird part. The f of a value must equal the f of b value. So wherever the starting y value is, let's say it's here, that has to be equivalent to the ending y value. So it doesn't matter what happens in the middle, but the starting y value and the ending y value are the same. Then Rolle's theorem guarantees us that at least one, but maybe more, c, x equals c, in our interval, let's add that one in there, c is in the interval a to b, the open interval from a to b. There's at least one c value in there, let's say right here, where the derivative at c, remember the equation, that would be the slope of the tangent line, is equal to 0. Actually, the function that I happen to draw here, it's certainly continuous and definitely differentiable, no cusps or corners. I have several values. I have more than one. There could be a c here also where the derivative, the slope of the tangent is 0. There's another one over here, but Rolle's theorem guarantees us that there has to be at least one value where if the two y values at the endpoints are equal, then there's at least one value where x equals c, or the derivative at that c is 0. Let me show you a proof of this theorem. Okay, for our proof, we're going to assume three things are true, the three conditions of Rolle's theorem. We're going to assume first that f is continuous on the closed interval a to b. We're going to assume that f is differentiable on the open interval from a to b. And we're going to assume that the y values match. F of a is equal to f of b. So the y values at the endpoints match. Now we know since we have a continuous function on a closed bounded interval from the last section, we know we can use the extreme value theorem. Remember, the extreme value theorem says that if we have a continuous function on a closed bounded interval, then we must have an absolute max and an absolute min on that closed interval. Well, these extreme values, the absolute max and absolute min, can occur at one of two places. They can either occur at the endpoints at f of a and f of b, or they can occur in between a and b. So let's look at case one. Case one was that f of a and f of b, so the end values themselves, are our absolute min max, absolute extrema. But we know that f of a is equal to f of b. Well, the only way that can be true is if f of a equals f of b, and f of a and f of b are the min and the max. That means that we must have a constant function. So f of x must be some constant. But we all know how to take a derivative of a constant. The derivative of a constant would be 0. So if we have case one where the endpoints are our extreme values, our absolute min and absolute max, then the derivative of the entire function is 0. So certainly there's a bunch of c's in there where f prime of c is equal to 0. So let's look at case two. Case two would be that the absolute min and max occur somewhere in the middle of a and b. So perhaps a graph that looks like this. Let's see, a to b, the y values must match. And draw my function in here. Continuous function. Oh, the derivative doesn't equal to 0. Ooh, I did not draw. I definitely have an absolute minimum here. So the extreme value theorem from the last section is fine, but this function that I drew does not obey the second condition to use Rolle's theorem, and that is that f must be differentiable or have a derivative that exists on the open interval from a to b. Now, we studied in the last section that you can have a min or a max when you have a function that the derivative doesn't exist at that point. But to use Rolle's theorem specifically, you need to have differentiable functions. So cusps and corners are not going to cut it for Rolle's theorem. So I need to fix my graph here. There we go. I have now both a continuous function from a to b and a nice smooth differentiable function. I sure drew a simple one, didn't I? From a to b. And it's nice and differentiable. There is at least one c value, looks like maybe right about here, at x equals c, where the slope of the tangent line or the derivative at c is equal to 0. So Rolle's theorem is satisfied. QED. One quick side note, the reason that we have to have continuity is because if I had a graph like this, so say I had a graph where f of x was a nice, and we'll start at A, and we'll go to B, but we'll make it discontinuous in here somewhere, so I'll have a little jump discontinuity, and it'll go to B. The reason that we have to have continuity for Rolle's theorem is here's a graph that is discontinuous. It might be differentiable at many of these spots, but it is discontinuous, and it does not have any location where the derivative is equal to 0. So in order for Rolle's theorem to work, you have to have three conditions. A continuous function from a to b, so not this one. A differentiable function on the open interval from a to b, so no cusps or corners. And you have to have the unusual stipulation that f of a must equal f of b. Then you know there's at least one c value where the derivative is equal to 0. Let's try a problem that uses this. Let's look at the function f of x is equal to x plus x to the negative 1 on the closed interval 1/2 to 2. And the problem that we're going to be asked to do is to find the c value guaranteed by Rolle's theorem where f prime of c should be equal to 0. Okay, the first thing that we need to do just before starting this problem is if we're going to use Rolle's theorem, we need to verify the three conditions that are required by Rolle's theorem are met. starting with asking the question, is f continuous on 1/2 to 2? Well, let's see, we have f of x equals, I'm going to rewrite this, x plus 1 over x. And this is discontinuous at one point. It's discontinuous at x equals 0. We can't divide by 0. But happily, x equals 0 is not in our interval from 1/2 to 2. So we're okay. Yes, this is a continuous function on the given interval. Okay, let's check condition 2. Condition 2 says that f of x must be differentiable on the open interval from 1/2 to 2. This tends to be the hardest one for students to understand. So here's how you check to see if a function is differentiable. For starters, take the derivative. So we're going to find f prime of x. And since f of x is equal to x plus x to the negative 1, its derivative is given by 1 plus, let's see, negative 1x to the negative 2, which I can simplify that. F prime of x is equal to 1 minus 1 over x squared. Whenever the derivative is itself discontinuous, that would make it not differentiable at that point. I'll say that again. Whenever the derivative is not continuous, is discontinuous, that means it is not differentiable. If the derivative is discontinuous, it's not differentiable at that point. So just like f of x itself was discontinuous when we were dividing by 0, f is not differentiable at the same actual location. It's not differentiable. I'm going to use my abbreviation diffable. It's not differentiable at x equals 0, which is not a problem for us because, again, x equals 0 is not in our interval from 1/2 to 2. This derivative does exist from those points 1/2 to 2. So yes, it is, it is differentiable from 1/2 to 2. Let's check the final condition. The final condition to be able to use Rolle's theorem is to check and see if f of a, so f of the first point, is equal to f of b, f of the last point. So let's check that. We would need to figure out f of 1/2, which is, let's see, we've got f of x was x plus x to the negative 1, so 1/2, plus 1/2 to the negative 1. Now remember, 1/2 to the negative 1 is 2, or 2 over 1. Oh, that's nice. And 1/2 plus 2 is, let's call it 2.5. Also, f of 2. So that would be 2 plus 2 to the negative 1. And 2 to the negative 1 is 1 over 2. Oh, there we go again. 2 plus 1/2 is 2.5. So yes, f of a does equal f of b. So now let's find that c. In order to find the c, where f prime of c is 0, we need to remind ourselves what f prime of x was. So let's see, f of x was x plus x to the negative 1. We just did the derivative a minute ago. That turned out to be 1 minus x to the negative 2. F prime of c is simply 1 minus c to the negative 2. And when we set that equal to 0, f prime of c equals 0, we have 1 minus c to the negative 2 equals 0. And all we need to do now is solve for c. Okay, let's go through and do that. That would be 1 minus, let's see, c to the negative 2 is 1 over c squared. I'm going to clear fractions, so multiply everything by c squared. And that's going to give me c squared minus 1 equals 0, which gives me c equals 1. Taking the square root of both sides, I have c equals plus or minus 1. So at first it seems like I have two x values that might work, positive 1 and negative 1. But remember, we're living in this interval up here, 1/2 to 2. So since negative 1 is not in the interval from 1/2 to 2, we only use x equals c is equal to the positive 1. Cool. So the x equals positive 1 is the c value where the derivative at c is equal to 0. That was guaranteed by Rolle's theorem. Now that we've done a thorough investigation of Rolle's theorem, we can extend this much more quickly to the mean value theorem itself. And I think the mean value theorem itself is best explained with a picture. So let me draw a graph. Now the graph I'm going to draw is going to look really similar to the graphs that we had for Rolle's theorem. Namely, we have to be continuous on the closed interval from a to b, and we draw a differentiable function on the open interval from a to b, but without the requirement that f of a has to equal f of b. So we can start and end at any two y values we wish to. I just need to make sure I draw both a continuous function and a differentiable function. So no skips or breaks and no cusps or corners. Okay, so let me do that to the best of my ability. Let's draw A to B. Cool. So there's f of A and f of B are different, so it's not like Rolle's theorem in the third condition. Then what the mean value theorem says is this: there must exist a c in between a and b where, now this is the different part, f prime of c is equal to the slope of the line between f of a and f of b. So let me get out a nice ruler and draw that line in there. There we go. Okay, so there has to be a c value somewhere where the derivative, or the slope of the tangent line, is parallel to this line. You know, I think I can see a couple of them. Let's say maybe like right here, I might get a tangent line that's parallel to that line. Yeah, a little help of the ruler, drawing a straight line there. So here could be one such c value. There might even be more than one. There might be one over here where the slope of the tangent line is also parallel. But the mean value theorem says there has to be at least one c value where the slope of the tangent line is parallel to the line between a and b. You know, we know algebra. We know how to find the slope of the line between these 2 points. That is just given by f of b minus f of a over b minus a. And there's our mean value theorem. If we have a continuous function on a closed interval that is also differentiable, then the slope of the line between a and b is equivalent to somebody's derivative, or the slope of the tangent line, at some c value in the middle. Let me describe this in terms of instantaneous rates of change compared to average rates of change. Examples I give a lot in courses where we're covering the derivative as an instantaneous rate of change compared to an average rate of change, say for a secant line, is I talk about velocity. So if I'm going to drive, let's say, 100 miles to get to San Francisco, then my average velocity, my v average velocity, would be 100 miles minus my starting point of 0 miles. And let's say I do this in 2 hours. So my average velocity is 50 miles per hour. And when I'm discussing derivatives with a calculus class, I make a big point that my instantaneous velocity doesn't always have to be 50 miles an hour. When I look down at my speedometer throughout my entire journey to San Francisco, I don't always see the speedometer reading 50 miles an hour. This is just my average velocity. But because velocity is continuous and differentiable, what I know is, at least at one point during my journey, at one point at least during my journey, I could have looked down to see my speed was 50 miles an hour. So at least one point during my journey, I had to have been going 50 miles an hour for at least one moment. So my instantaneous velocity for at least one moment had to somewhere have been equal to the average velocity. Now, if my average velocity is 50 miles an hour, I can't say that about any other instantaneous velocity. If my average velocity is 50 miles an hour, I can't guarantee that I was ever traveling 60 miles an hour or 40 miles an hour. I just know that I was traveling at least at one point 50 miles per hour. Let me show you what this looks like for problems that we'll find in our homework. Okay, let's let our function f of x be equal to the square root of x on the interval from 1 to 9. And let's find the c that's guaranteed by the mean value theorem. Okay, so if we're going to do this, the first thing that we need to do is to check and see that we can use the mean value theorem in the first place. So we need to check and first see if f is continuous. Now, since f of x is equal to the square root of x, that has no skips or jumps in it, that is definitely continuous on the interval 1 to 9. The second thing we need to look for is if f is differentiable on 1 to 9. Now, this one's going to take a little bit more math to do. Let's see. F of x, I'm going to rewrite this in a more derivative-friendly way as x to the 1/2. When I take the derivative to check and see if it's differentiable, f prime of x is 1/2 x to the negative 1/2. And then I need to see where it's discontinuous, so I'm going to rewrite this as 1 over 2 times the square root of x. Now, really similarly to our previous problem, this function is only discontinuous at x equals 0. Therefore, it's only not differentiable at x equals 0. So when the derivative is discontinuous, that's when we say it's not differentiable. Our derivative does not exist at x equals 0. Therefore, it's not differentiable at x equals 0. But luckily, 0 is not in our interval from x equals 1 to x equals 9. So we're good to go. So the answers to both of the first two questions are yes. Our two conditions are met. It's continuous on the interval from the closed interval from 1 to 9 and differentiable on the open interval from 1 to 9. If, by the way, this had been going, let's say, from 0 to 9, or I'm sorry, from -1 to 9, which I get would not be in our domain here, but if for some reason the 0 were in the interval, we cannot use the mean value theorem at all. But in this case, both conditions are met, so we can. So now let's find the c. So remember, in order to find the c, we need to find f prime of c that is equal to f of b minus f of a over b minus a. Okay, well, a few minutes ago, we found f prime of x. So let me write this over here. We knew that f prime of x is 1 over the square root, 2 times the square root of x. So f prime of c is 1 over 2 times the square root of c. 1 over 2 times the square root of c. On the right-hand side, f of b minus f of a, so that would be f of 9 minus f of 1 over 9 minus 1, b minus a. Let's see, f of 9 is square root 9. F of 1 is square root 1 over 9 minus 1. So we have 3 minus 1 over 8, or 2/8, 1/4. So we have the derivative is given by 1 over 2 root c, but the slope of the line between the 2 points is 1/4. And all we have left to do now is solve for c. Okay, let's clear fractions. So I'm going to multiply both sides of this by 4 times the square root of c. That's our common denominator. So the root c's will cancel here, and 2 goes into 4 twice. On the other side, the 4's cancel, but not the c's. So what I'm left with is 2 is equal to the square root of c. Squaring both sides, I get c equals 4. So if you look at this, what that means is let's see, if I were to draw a really quick graph of this. God love Desmos. Here is a graph of the square root of x from x equals 1 to x equals 9. And it's very, for lack of a better word, liney at this point. So if I were to draw in the secant line between the two, it might look something like this. Hey, not so bad. All right, so there is my f of a minus f of b over b minus, f of b minus f of a over b minus a. That is the average rate of change here. And what this says is that at x equals 4, that's the exact location where the slope of the tangent line, there it goes, the slope of the tangent line right there at x equals 4, so f prime of 4 has a slope of 1 over 4, plugging it in here, as does the slope of the secant line between the two endpoints. Also has a slope of 1/4. There is a great sample problem for finding the c guaranteed by the mean value theorem.